So we now know how to calculate the pH of a weak acid or a strong acid. The next thing we want to do is what happens when we have mixtures of acids. Now, this material is not in the OpenStax textbook, but it is material that we will have on tests and quizzes for this class, so be sure to be paying attention. It is in other textbooks, so if you're looking for other resources, there's plenty of resources for it. For whatever reason, they decided not to include it in OpenStax. So when I first made these slides, I did a Google search, and I said, mixing chemicals. And these were the first two images that popped up. And I thought it was interesting because really, Google tries to do a job where they rank kind of by popularity, essentially. And so these were the two pictures that Google thought, or other people who perused for pictures, thought were the most indicative of people mixing chemicals, which is two scientists mixing colored chemicals with weird, strange faces and no goggles. Okay, so that is the media perception of scientists in this world, and that is the perception that you, as future scientists, are going to have to deal with, right? So we are sometimes a little strange, right? You've watched my videos now, but really, at least wear goggles. So I just thought it was interesting. What we're going to talk about is what happens when we have a solution, and it doesn't just have one acid in it, right? Before we were saying, oh, we've just got HA or we've got HCl, but what if it happens two acids in it? So we're going to do HA and HB. What's going to happen to the pH of something when there's a mixture of acids? So a few different scenarios here. One is, let's say we're mixing two strong acids. So here we've got 0.10 molar HCl, and we're going to mix it, and we now have a solution that's 0.20 molar in HI. So we've got both of those in the same solution. There's no dilution or whatever. The same solution has 0.10 molar HCl, and it has 0.20 molar HI. If we recognize both of those as strong acids, which you should because you've memorized those by now, if we recognize those as both strong acids, we know that they're going to completely dissociate. So this is going to be 0.1 molar H+, and this is going to be 0.2 molar H+. And so it turns out we can actually sum these in order to find that we're going to have 0.30 molar H+ in solution. Because they're both strong, they completely dissociate. And if you think about it in molecules, if we had one molecule of HCl, two molecules of HI, we'd end up with three H+ in solution, 3 atoms of H+. So if we wanted to find the pH, right, we just take the negative log of that, negative log of 0.30, and you'd get 0.52. Okay, so that's how we'd find the pH of a mixture of strong acids. Next, let's talk about a mixture of weak acid and strong acid. So here we're going to have something like HCl mixed with HNO2. So we've got a strong acid, or let's do a different one we haven't done in a while, HCN. Okay, so we're not going to, strong acid and a weak acid. And let's say we have 0.10 molar HCl and we've got 0.20 molar HCN. What's going to happen? This one is going to contribute 0.10 molar to my H+, because it dissociates completely. We recognize that as a strong acid. This one, what it's going to do? Well, it's certainly not a strong acid because we know it's not on the list of strong acids. How weak is it? We look up the Ka value for that one, and it's 6.2 times 10 to the minus 10th is the Ka. So how much is that going to dissociate? You remember even for or acetic acid, I think, which was a relatively strong acid, we got 0.42% dissociation. Very, very little. So if we're getting very, very little dissociation from this guy with the Ka of 10 to the minus 10th, which is much weaker than acetic acid, how much H+ is it going to be contributing? Maybe, 0.001%. So we're talking about 0.0002 molar or something like that. That's not even in significant figures of this one. And so when we have a strong acid and a weak acid, what we can very easily do in almost all circumstances is ignore the weak acid and just use the strong acid. Now it says strong, and it should say strong. Just use the strong acid. And so our pH is just going to be the negative log of the concentration of H+, which only comes from our acid, our strong acid, and so it is 0.1. And so we get a pH of 1.00, like that. So that's our pH, 1.00. And we have piano music accompanying this wonderful revelation about pH in strong and weak acids. All right, so 2 easy cases so far. Strong acid, you combine the 2 strong acids. Strong acid and weak acid, we ignore the weak acid, and we just use the strong acid. How about the case of a weak acid plus a weak acid? So we're going to do HCN just like we did in the last one, which we know goes to H plus Cn minus. Those are all aqueous. And we're going to combine that with nitrous acid, HNO2, H plus NO2 minus. And we'll also just remind ourselves that in all of this, water is also autoionizing, and so we have the contribution from water as well. So we actually have 3 different simultaneous equilibria. Ooh, what are we going to do? Well, we're going to look at maybe what's the contribution of each one of these. So we're going to look up K values for each of them. We already had it for HCN. The Ka value was 6.2 times 10 to the minus 10th. This K value is 4.0 times 10 to the minus 4th. And this one is 1.0 times 10 to the minus 14th. So 3 different Ka values and very different orders of magnitude, right? 10 to the minus 10th, 10 to the minus 4th, 10 to the minus 14th. Let's focus on the higher 2 for now. 10 to the minus 10th, 10 to the minus 4th. If I was thinking, hey, which one of these is going to be contributing a lot more H plus than the other one, what would I do? I'd say, well, 10 to the minus 4th, when we square root that, excuse me, that's my first sneeze on camera, I think. When we square root that and to multiply it by the concentration, whatever we do with our small x assumption, we're going to get a lot bigger number than we would in the case of 6.2 times 10 to the minus 10th. And so we might make the assumption that this one is going to be contributing most of my H+. In fact, that ends up being a very, very good assumption. When we have several weak acids, it's only the strongest one that's going to make the most contribution to H+. And it's possible to actually go through and calculate the contribution to each one of them, but we're not going to do that too much in this class. We're going to say, hey, the strongest one is going to contribute most of the H+. So let's focus our pH discussions on that one. So we're going to do a pH on that one. So even if we had a 5.0 molar HCN, then we're going to have a 5.0 molar HNO2. What we're going to do, because HNO2 has a much larger Ka, is we're going to use this one and we're going to ignore this one, at least in terms of its contribution of H+. It's still there, it's still doing things, which we'll see in a little bit. But we're going to ignore its contribution for our hydrogen ion concentration, and we're just going to focus on our HNO2. So we get HNO2 goes to H plus NO2 minus. We start with 5.0 molar, 0 approximately. 0, right? Remember approximately because water does contribute some, and in this case the HCN is also contributing some. Minus x, 5.0 minus x, we get Ka equals 4.0 times 10 to the minus 4th is equal to H plus NO2 over HNO2, which is just going to be x squared over 5.0 minus x. We're going to go ahead and make that small x assumption. And we get x squared is 5.0 times 4.0 times 10 to the minus 4th. And if you solve that, you just get that x is 0.045 molar. Let's check our assumption. We haven't been doing that well, right? 0.045 molar divided by 5.00. Let's go ahead and check that. That is 0.9%, which means we're good. Okay, so 0.9%, that is a good assumption. All right, so now we can continue on. X, that was our H plus concentration. 0.045 molar. And we said, hey, that's going to be most of the H plus that's in solution. So we can go ahead and find out that the pH is then equal to 1.35 by taking the negative log of that. So we have a very low pH, a very acidic solution. Not surprising since we had such a high concentration of that acid, 5.0 molar, that we'd get a very acidic solution. Now, what we want to do is ask another question. So we identified the pH of this solution, but we're going to ask a second question about this solution. We want to know what is the concentration of the cyanide ion in this solution, in this mixture of acids. What is my cyanide concentration? You say, well, professor, we know how to do that. We can do HCN goes to H plus CN minus, and we do our ice table 5.0, we do our approximately 0, we do our 0, great, we do our x's and things like that. But I have to stop you here and say, well, what did we just calculate? We just calculated that somewhere in the solution, something is producing 0.045 molar H plus. Is the HCN going to see that? Well, yeah. Whether we have the HCN at the beginning, whether we have it at the end, when it's all mixed together, the HCN is in a solution that is 0.0545 molar H plus. And we can't ignore that. We can no longer say that it's approximately 0 because it's just the contribution from water. We have to say that this is 0.045 molar. Okay? You have to think about that for a while if you need to, right? But it doesn't matter. Let's say we started with just a solution of HCN, and then we added the other acid, our nitrous acid. When we mixed it together, the nitrous acid would be contributing 0.045 molar. If we started with the nitrous acid and mixed H in the HCN, the nitrous acid would be contributing 0.045 molar. So it doesn't really matter the order that you add these things in. What matters is when they're mixed, they see what everybody else does. So the HCN sees the contribution from the nitrous acid, and we've got to put that in there. There's still no cyanide ion, so we still know this is going to go to the right. And so that's our ICE. We get 5.0 minus X, 0.045 plus X, and X. And now we get our Ka, which is 6.2 times 10 to the minus 10th. That's going to be H plus Cn over HCN. And that's going to be 0.045 plus X, X, and 5.0 minus X. Now, we can solve that exactly. It's a square. We could do the quadratic formula. Let's see if we can use the small x assumption. We're not sure, but you know that k is pretty small. And that k pretty small tells me that I'm probably not going to make much product, right? That's what a small k tells me. And my product is my x here. So let's just try it. Let's go ahead and use the small x assumption and see what we get. And we get 6.2 times 10 to the minus 10th is equal to 0.045 times x over 5.0. Wow, there's not even a square anymore. That's cool. We took out our square entirely. And so you get that x is equal to 6.89 6.89 times 10 to the minus 8th. Well, that's a very small number. We can look back up. We were doing our small x assumption. We were comparing that both to 0.045 and to 5. 10 to the minus 8th is sufficiently small that I don't even need to divide that. I can say it's an obviously good assumption. And you can do that when there's several orders of magnitude between your x that you calculated and your numbers that you're comparing it to. If you're not sure, if it's like, oh, it might be 1%, it might be 0.5%, it might even be 0.1%, you should do the calculation and show that result. But when we're talking 6 orders of magnitude, 4.5 times 10 to the minus 2 to 6 times 10 to the minus 8, we're good. We don't have to actually do that calculation. We can say it's obviously a good assumption. But it's good to write that because it says to me, hey, I checked my assumption. All right, so there we go. X is 6.89 times 10 to the minus 8th, and that is also my Cn minus concentration. 6.9 times 10 to the minus 8th molar. Wow, that's a very small concentration, not very much cyanide ion in this system. If you did HCN all by itself, you would have gotten a much larger cyanide ion concentration. All right, so in order to calculate H plus of an acid mixture, what you have to do is ignore the weak acid and just focus on the stronger weak acid. Right? So ignore the weaker weak acid and pay attention to the stronger weak acid. Then, if you want to calculate one of the concentration of the ions of one of your weaker acids, you use the contribution of H plus from the stronger weak acid, that was our 0.045 that we calculated and used in our initial line in our ice table in order to fill in your ice table. And then you just do the small x assumption if it's valid, and the math ends up being very easy. So we get 6.9 times 10 to the minus 8th molar, a very small amount of cyanide in this system. Nope, that was supposed to get removed. Okay, so here we've got a question for you. Which acid will determine the pH in a mixture of phenol, which has a Ka of 1.3 times 10 to the minus 10th, benzoic acid, 6.5 times 10 to the minus 5th, hypochlorous acid, 2.9 times 10 to the minus 8th, and water, 1.0 times 10 to the minus 14th. All righty. Okay, what'd you come up with? Well, hopefully you said, hey, look, I've got a mixture of acids here. Now, Professor Clements only put in 2 acids, and now he's making me do 3 acids, but it doesn't matter. You can do 12 acids. You're primarily going to focus on the one with a significantly larger Ka value, which is going to be, in this case, the benzoic acid. It's 3 orders of magnitude bigger than the Ka for HClO, and it's probably going to dominate your H plus contribution. And so you can say with some certainty that the benzoic acid is going to be the primary one. Now, here's a question. In a mixture of phenol, benzoic acid, and hypochlorous acid, same as the last problem, what is the concentration of ClO minus? Will it be larger or smaller than a solution with only HClO? And let me draw that for you so you know what I mean. I mean, here we've got our mixture, and it's got our HClO, it's got our phenol, it's got our benzoic. Or we've got a solution that's just HClO. Okay, so it's just HClO. And I want to know which of these two is the ClO minus larger. Is it larger in the one with the mixture, or is it larger in the one that only has HClO? Okay, so your turn. What'd you think? Well, when I think about it, I look back at that problem with the cyanide, and I said, hey, when I had that other acid in there, I ended up with a very small amount of cyanide because my ice table, my Le Chatelier's principle, said I've now got all this product, it's going to shift my equilibrium to the left a little. Same thing here. My benzoic acid, which is going to dominate, is going to put a lot of H plus into solution. That H plus, the HCl is going to look and be like, hey, there's already a lot of H plus in here. Le Chatelier says, I'm going to stay on my side. I'm going to stay on the HClO side. And so you're going to have not as much HClO dissociating and a smaller concentration in this one and a larger concentration of ClO minus in this one. So the concentration of ClO will be smaller in the mixture than it is in the one all by itself. And you could do the calculations to prove that to yourself. You could absolutely do that calculation. Just pick, equal concentrations of 0.1 molar for all of them and do the calculation, and you'll find that's true. Or you can just kind of think about it. Be like, hey, Le Chatelier's principle said when I've got H plus here, it's going to shift my equilibrium back to the left. I'm not going to make as much ClO minus. All right. Hope that introduction to acid mixtures was useful. Strong, strong, you add. Strong, weak, just do the strong. Weak, weak, just do the stronger of the weak. And then if you want to find out one of the ions in concert with that other weak acid, you have to use the H plus from the stronger as an initial in your ice table for the weaker. And you find out that there's very little dissociation of your other weak acids. They're contributing very, very little to the overall equilibrium. Thanks so much. Have a wonderful day.